Anyway, today what I want to talk through is this idea of what a function is. Okay, so essentially we are starting the mathematics mathematics part of the module. So there's 6 themes in mathematics. Okay, we're going to start with this idea of differentiation, but before we get there, I want you to understand what a function actually is. Yeah, that's fine. I want you to understand what a function is. Now, does anybody actually know what is a function?
A form of
something that takes input output. So.
Absolutely right. So a function literally is a mapping from an input onto an output. Okay, so that's literally all I want you to think of. That is all a function is. Okay, and in fact, you've probably seen this before, like in primary school or something, as a function machine. Okay, so a function machine literally takes, in this case, a value, like we're in maths, it takes a value, a number, it does something to that number, and then it generates a number which spits out. Does that make sense? Okay, so an example might be multiply by 2. So that's my function, multiply by 2. So for example, if I stick 3 in this side, that's my input, what's my output going to be? 6. If I stick negative 10 in this side, what's my output going to be?
Negative 12.
Negative
20, sorry.
Negative 20, good, excellent. Okay, so a function literally takes a value, it does something to that value, and then maps it onto an output. Okay? Let's streamline this a little bit. Okay? I don't want to have to write input and output every single time, so I need to come up with a letter. What letter shall I give for my input? Why not? Okay, it can be anything you like, but why not say X? What letter shall I give my output? What comes after X?
Y.
Why?
Y. So in general, we say that Y is the letter that represents our output, and my input we represent by X. But you're right. In here, I have my function. So the way to think about it, I'm going to give my function a name. In this case, I'm just going to call my function f. F for function. It could be anything you like. It could be Eric. It could be shouting. It could be anything you like. All right? But in this case, I'm just going to call it f. And what I do is I apply my function to my input. Okay? So I would say this as f of x. Okay? In other words, my function is being applied to my input. Right? So in order to get my output, y, I have to apply my function to my input. So I'd say y equals f of x. Does that make sense, that notation there? It literally just says you take an input, you apply some function to it, and you get your output out the other side. Okay? But in this case, what is my function in terms of x if I just multiply my input by 2? 2x. Does that make sense? Yeah? So it's kind of quite confusing notation, but it's a really simple idea. Really simple idea. Okay? So let me give you another one. Okay, so as an example, let's say that y is equal to f of x again. So this is my function, and I get my output y like this. And let's say that my function is 3x squared plus 4. 3x squared plus 4. So just pause for a second. What does this function tell me to do to my input? So what am I doing to my input? So first things first, I square it. That's what I need to do first. Then I'd multiply by 3. Then I'd add 4. Okay? So, what would f of 2 be? So in this case, what's my input?
16.
What's my input?
Oh, 2.
2. That's the thing which goes there, right? The x represents my input. I'm applying 2 to my. I'm putting 2 into my function. Okay. So therefore, all I need to do is put 2 through this thing. It literally is just a rule. Yeah. So I need to square it first, then times it by 3, then add 4. So sorry, what do I get? 16. That's my output. Does that make sense?
Yes.
Yeah. What would f of 5 be?
I mean, we do this similar thing in expectation algebra, right?
Yes, exactly that. Yeah, exactly that. So you can kind of think about expectation and variance as a type of function. Yeah, absolutely. What would f of 5 be?
79.
Good, so I need to square my input first, become 25, times by 3 to become 75. 5, add 4, it would become 79. Does that make sense? Yeah? Okay, so have a look at the screen then. I think I can pick it up on there. What I want to do is I want to illustrate this mapping. Okay? So I have an input. By the way, I have a set of inputs. So the set of numbers that I can put into my function, does anybody remember, or does anybody know, what I call the set of inputs that I put into my function? Begins with a D. Not quite. It's domain. Okay? So my domain is the set of inputs that I can put into my function. Does that make sense?
Yes.
Right? The set of outputs which I can get is my range. Okay? So my domain is the set of inputs that I can put in, every single possible value of x that I can put in, and my range is the set of possible outputs. So as an example, just over here, okay, if I have my function, so y equals f of x, and if my function is, in fact, just to illustrate the point, I can call my function anything I like. So I'm just going to call it g instead. So my function is g of x, y equals g of x, and my function is going to be x squared. Okay? What is my domain? What is the set of possible input values? What's my domain?
X.
Hmm?
X.
So is there any restriction on the value that I can put into my function? No. So I could write this as every single real number. Every single real number. So you can either say it in words, all real numbers, or you can use the shorthand notation which says that x, my input, is an element of the set of real numbers. Okay? All this just basically means is I can put every single number I like, as long as it's real, into my function. Okay? But what's my range? What's my range? Remember, my range is the set of output values.
True.
Start from 0 and then moves off in which direction? Positive. Yeah.
Direction.
So I would say that everything greater than or equal to 0 would be my range. And if you're sitting there thinking, why does that make sense? Have a think about the graph of x squared. Okay, what does the graph of y equals x squared look like? It's a parabola
Yes. W.
that sits at 0, sits at the origin. Okay? So are you happy that I can put in, if x, this is my input, okay? Are you happy that there's no restriction over the input value? I can put anything I like in. But if you have a look, my output values, they're only going to be positive or 0. In other words, non-negative. Does that make sense?
Yes.
Of sorts, okay? Now to explore this idea further, have a look at the screen. Okay? So I'm literally mapping this idea of inputs and outputs on the screen. Okay? But I'm doing it in a slightly different way to what you may have seen before. So on the top, I have a number line. Okay? So all it is, just a number line. And on the bottom, I have another number line. But the idea is, the top number line represents my input value. So in this case, I've just arbitrarily chosen negative 3.4, that's my input value. Okay, do you see that? Okay. Then the bottom one is my output number line, and the idea is that if I put negative 3.4 into my function, by the way, my function in this case is 1 over x, I've just chosen that arbitrarily. Okay. If I put negative 3.4 into my function 1 over x, I would get out something close to negative 0.5. Okay? That's all it means. Does that make sense? Right? And in fact, I can move this around. Okay, so I can change my input value. So instead of doing like negative 3.4, let's say, for example, do negative 1. Okay? Now, are you happy that if I stick negative 1 into my function, I should get negative 1 out? Okay, so I'm just really illustrating this mapping. I'm taking an input, and it maps to an output under this function, under this rule. All right? But what happens then if I do this for multiple values, okay? So you can kind of see what happens as I move it around. It tends to grow quickly at some points, and then it tends to grow less quickly at other points, okay? So you can see, for example, values close to 0, it grows really, really quickly, but then as I move away from 0, it starts to grow much, much slower, okay?
And goes towards to 0.
it goes towards 0. Yeah, absolutely, absolutely. And in fact, if I show this as a sort of loads and loads of values, I would get something that looks like that. Okay. Which I think looks quite pretty. Yeah, I think it looks quite pretty. So remember, all I'm doing here is I'm choosing an input value, and it maps to a unique value on the output number line. Okay? But I'm doing it for sets. A set of values of the input and a set of values for my output. Okay, so I get a pretty picture. Does anybody know what the graph of y equals 1 over x looks like? Does anybody know? No? Okay. So I can do something that looks like this. It looks like that. Has anybody seen that before?
Yeah.
Yeah? It's that graph there. So how on earth does this thing relate to this thing? How on earth does this thing relate to this thing? Well, let me show you. Okay. So let me just choose 1 over x again. So here is my mapping, same as before. Here's my mapping, same as before. I've condensed it in slightly, but it's still 1 over x. Okay. Well, all I've got here is just two number lines. A number line for my input and a number line for my output. So what I'm going to do is make a bit more efficient use of the space here. Instead of just having two number lines that parallel to each other, why not utilize the two-dimensional space a bit more efficiently? In other words, why don't I take my output number line and rotate it through 90 degrees such that it intersects the input number line at 0. Let me show you what I mean. Okay? So watch the screen. I'm literally just going to rotate the output number line so that it's now intersecting there. Does that make sense? Okay. But you see, the thing is, at the moment, if I hide that mapping, at the moment, I'm not really making best use of that two-dimensional space. Because all I'm still saying is that value on my input number line gets mapped to that value on my output number line. Yeah? So why not make use of all this extra 2D space over here and over here and over here by saying, well, let's just define one point. Instead of defining 2 points, this point on my input number line and this point on my output number line, let's define it as 1 point. Namely, the distance which that point is across, so in the horizontal direction, is defined by my input. And the distance which my point is up or down is defined by my output. Okay? So, in other words, this point here is the point which I'm interested in. Okay? Where the distance left or right is defined by my input, and the distance up or down is defined by my output. Okay? And you can still see the same kind of thing is happening. Okay, so I'm just changing my input now, I'm just seeing how my output changes, but I'm now mapping it as a single point. Does that make sense to everyone?
Yes.
Now, if I join all of those points together, would you be happy that I get this graph? I get the 1 over x graph. You might not be able to see it very well on here, but I get this graph here. So all I want you to think about as a graph is it is a set of points that follow some rule. Okay? So this here is not actually a line, it's actually the set of every single points that you can get under this rule. Does that make sense to everyone?
Yes.
Yeah? Okay.